Hi, our topic is development of RM device for neuromorphic system application. The content first is introduction, second is operation of RM device, third is how to make RM device, and fourth experiment results. First is introduction. This figure is so-called the von Neumann structure. Processing units and memory units are physically separated. The problem is the von Neumann bottleneck will occur, which limit the treatment of enormous data. So we want to solve this problem, and we figure out the neuromorphic computing. It is mimic the brain of human and the co-located processing and memory. It communicates with spikes, not binary data. So we want to mimic the human brain using neuromorphic computing using an RM device. Second is operation of RM device. This figure shows the general process of the RM storing data storing process. This is the initial state. It's an as prepared device and it has no conducting filamentary path. The first one is the forming process. As we apply more than a threshold voltage, it forms a filamentary conducting path, and the whole device resistance is much lower than initial states. So this graph's green one is meaning that the IV curve of the forming process. After that point, it leads. And second one is reset process. As the filamentary path is in the device, the current is increased as we apply the voltage, but after threshold voltage, it decrease, and which means that the rupturing of the filamentary path. Third one is set process. At high resistive states, if we apply a set voltage and the ruptured filament was restored, and the whole device's resistance is higher than reset states. This is a typical IV curve of RM device. So this is the high resistive states, which is the much lower than the low resistive states current. After a set voltage, the current leaves, and the whole device is become the low resistive states. So the curve is drive like that, and after the reset voltage, it decrease about 3 or 4 orders and become high resistive states. Both states are non-volatile states, and we can store information with the high resistive and low resistive states. Third, how to make. We use a solution process to depose the zirconium oxide thin film. So we calculate the exact amount of the material. We use the zirconium chloride octahydrate 1.289 gram and 2-methyl ethanol 4.89 grams. It is a 0.8 mole of zirconium oxide. This is the figure of our RM device. It is a sandwich device. The bottom electrode in here, and at the middle there are zirconium oxide thin film. At the top there are top electrodes. So first, the aluminum bottom electrode is deposited using an avium evaporator. Second, we depose the zirconium oxide using a spin coater and solution. Third, the aluminum top electrode is deposited using an avium evaporator with mask. Fourth, experiment results. The only energy source of solution process is thermal energy of post-annealing, so the optimization of post-annealing temperature is very important. So we compare the 200 Celsius degree and 400 Celsius degree of post-annealing temperature. So this is the result. The left figure is show the leakage current of each thin films. The red one is 400 treated thin film, and the black one is 200. As you can see in this graph, the 400 device is much lower leakage current than the 200 ones. The white one is a capacitance. The green one is 400 degree and the black one is 200 degree. The green one, the 400 device, is much higher capacitance than the black one, the 200 degrees. So we can result that the 200 degree is not good for the annealing temperature, so we eliminate the 200 degrees Celsius as a candidate. We also compare the 400 and 500 degrees Celsius. The left graph shows the leakage current of each thin film. As you can see in this graph, the 500 degree has lower leakage current than 400, and as you can see in the right graph, 500 thin film has much lower than the 400 degree thin film. So the 400 degree films has more leakage current and more capacitance. Although 500 has lower leakage current, but 400 has almost doubled capacitance, so we conclude 400 is the most optimized temperature. But why 400 degrees Celsius has higher capacitance than 500? This is the XRD peak of two thin film. The red one is 400 and the white one is 500. Because 500 ReRAM has a tetragonal peak. This is a tetragonal peak of the 500 degrees. This is an AFM picture of two thin film. The left one is 400 and the right one is 500. As you can see in this picture, the cell-like structure is a locally crystallized structure, which makes the grain boundary and leads to the limitation of the movement of electron and lowering the capacitance. So we review the ReRAM for neuromorphic computing. Thank you for your attention.